So the next speaker is Abigail Bodner. She is assistant professor in shared between the departments of Earth, Atmospheric, and Planetary Sciences and Electrical Engineering and Computer Science. Before joining MIT, she was Simon Society Junior Fellow and working at the Courant Institute of Mathematical Sciences in New York University, and also an affiliate, and I love these acronyms, the Multi-Scale Machine Learning in Coupled Earth Systems Modeling, or M-squared lines. I like that. So please help me welcome Abigail.
Okay, I broke it. Hi, everyone. So that was a pretty phenomenal talk. We're going to switch into quite a different angle to understanding climate and climate change. So as mentioned, I'm shared between Earth Sciences and the College of Computing. And kind of the angle that I'm after is trying to understand how can we improve climate models and climate projections into the future. And I do that by focusing on very small scale processes within the Earth system. So as many of you probably already know, the climate system is a very complex system. It involves interactions between the atmosphere, the ocean, land, biology, as we just heard, ice, anthropogenic forcing, and all of these are happening over an extremely wide range of scales. So we've got centuries worth of atmospheric circulation, for example, and we can have really daily interactions between small scale features. And if we try to simulate these in climate models, so these are called, these are known as general circulation models. We're trying to basically reduce the complexity of the world to simulate a world, right? So we have to think of what are the first order most important processes that we know are relevant, for example, for temperature rises for the next 100 of years. And we're limited, right, by resolution, by time stepping. If we're running a model 100 years into the future, that's pretty massive. So any process that's too small, too fast, or too complex doesn't really make it into the model, despite some of these processes being really important for the climate system. So what we do is we basically trick the model, and we account for them by what's called a parameterization. So a parameterization is like a reduced order complexity mathematical expression that we can code up into the model, but it doesn't burden the simulation. We can still forward it in time, 100 years, for example. So I focus on the ocean and the angle of how do small-scale ocean processes that are extremely important for the climate system, where there's a lot of sensitivity in terms of heat flux, for example, and CO2 emissions, can better be represented in climate models from what we're doing right now. So the IPCC report, which is what most of us use in order to understand climate change into the future, normally we have these kind of three different scenarios. We've got the best case scenario where we completely shut off emissions right now, and then we've got the business as usual where we keep going, and there's a very widespread in terms of what's going to happen by 2100. And even though there's a widespread between scenarios, you might notice that there's also very widespread in terms of what the projections are. So for example, if you follow the red line, which is the average of business as usual, there's a very widespread in what the climate models say is going to happen. And the reason there's such kind of disagreement in projections is mainly due to these parameterizations. So how different models treat unrepresented processes or unresolved processes in climate models. So the hope is to try to reduce these biases, reduce these discrepancies by improving physics at the small scale. And that's the focus of my work. So I focus on what's called the ocean mixed layer. The ocean mixed layer is the uppermost layer in the ocean. It directly interacts with the atmosphere. So if any of you have gone to the beach 6 months ago, you would have noticed there's a lot of wind and waves. Temperature could change. And all of this is affecting how much turbulence or how much mixing occurs at the ocean surface. And the reason that's so important from the climate perspective is that heat and carbon and all these other important parameters that affect long-term projections of climate change have to be transmitted between the atmosphere and the ocean through this uppermost layer. So there's a whole lot of sensitivity, some might say even a tuning parameter in this uppermost layer that will affect projections into the future. And there's a lot of work by the community to try to understand and better represent these small-scale processes. They tend to be very small, very fast, very complex, so naturally they go unresolved in climate models. So just to bring this point further, what we're seeing on the top left is the North Atlantic. This is what's thought of as like a standard ocean model, the same that get used, for example, for the IPCC report. It's pretty hard to see where Boston is on the map. It's about 100-kilometer resolution. Oh, I'm just going to click play. So this is sea surface temperature, and it's being kind of swished around in the ocean. We don't really see the Gulf Stream, even though we know it's there. We don't really see small vortices called eddies, which are supposed to be there. So all of those processes fall below the grid scale, are called subgrid, and they are parameterized. This is what's thought of as the next generation ocean model. So it's a 10-kilometer resolution. We can see Boston a little better now. And we can see these eddies. We can see the Gulf Stream now. And this looks a little more realistic. If we were to zoom in a little further on the North Atlantic, what we're seeing now is what's known as a regional ocean model. It has a 1.5-kilometer resolution. And this, what's plotted here is vorticity, which is the rotation of the flow. So you can see there's a lot more fine-scale structure coming out now. We can see some multi-scale interactions, so vortices of different sizes, some mean flow going on. There's really a lot more happening over there. If we were to zoom in even further to the Chesapeake Bay, this is a 500-meter resolution. And once again, we just go finer and finer grain in this flow. And these are the processes that I'm after. Okay, so you can see that they're very far from what we need for the climate models. We're talking about 50 to 100 times more resolution. And the question really is, what is the most important process? How do we capture kind of all of this complexity into a single grid point? And how do we utilize our information and a physical understanding in order to make sure it's really the right information needed for climate projections into the future? So unfortunately, we're very limited with observational data at these scales. So there are a whole lot of different cool instruments. Some even involve sea mammals. I don't do that kind of work, unfortunately. But there's a lot of different instrumentation, and there's a whole global distribution of it. But unfortunately, scales that are around 1 kilometer are really hard to measure. They're very fast. They can occur kind of in the order of a day. So you really need a very dedicated observational campaign to get the information about those scales. So we're really limited in what we know about the very small scale ocean flows. So a lot of work goes into theory, goes into simulations. And we've got some very rare satellite imagery also that we can use. And this here is a really nice image of chlorophyll in the ocean. So it kind of highlights how the ocean surface is important for productivity in the ocean and nutrients, because all of that's really happening kind of where the light's being come in and where winds and waves are active. So these are submesoscale. That's kind of the official name of the range of scales that I'm interested in. They're about 1 kilometer in scale. You can see they have these cool features like eddies are those little vortices. A front is a very sharp interface in density. Fronts are extremely important for ocean-atmosphere interactions. They're like the lungs of the ocean. It's where the atmosphere will essentially transmit carbon and heat, and they go through these density surfaces into the ocean interior. And there's a lot of effort in trying to understand how these fronts, how you can really simulate them and add them into climate models and parameterizations. And those are filaments, which are like elongated streaks, or kind of like a hair in the ocean, and they also kind of have a similar feature to fronts. So interestingly, fronts are, as I mentioned, they're kind of like the lungs of the ocean. And we don't really understand very well the physical mechanism behind them. We don't also really understand their scale. And that's been an enigma for decades, really, because we haven't been able to really write down the mathematical formulation that really is able to explain how wide do they get. And just to illustrate that, on the top left, we see that's a front in the Gulf of Mexico. So we have the warm, fresh Mississippi River pouring into the cold and dense Gulf water, and we get these very sharp interfaces. So we're talking about like a single meters. On the contrary, also in the Gulf, we have the Deep Horizon oil spill, I think it was 2011, where a ton of oil spilled into the Gulf of Mexico, and it was transported along these fronts. So you can see that in that top right image over there, and notice just the difference in scale between this front carrying the oil in the ship versus that same location where we see these very, very small fronts. Fronts are also important for transporting oil and sea ice. So we have sea ice from the Arctic over here that's being squeezed in between these larger eddies. And if you were to look at a transect of a front, what we can imagine happens is that we have nutrients that live along these fronts. So they're very important for marine biology, for example. So part of the work I was doing a few years ago was I was trying to really understand how we can improve this in climate models because they're such a small process, but they also have such a large impact on climate models. So if you stare at these long enough and you think of some equations, you can actually come up with different physical laws that represent how we understand fronts, both in a more theoretical representation and in high-resolution simulations, where we understand how upper ocean dynamics and how they interact with all the other types of turbulence that are in the ocean. So I'm not going to get into this too much, but just kind of as a primer for what is like the standard or like the background for my work with more machine learning computing stuff. So once you think of this new scaling law or new physical law for parameterization, you then want to say, well, what is the impact of this on the climate system? So recall that these processes are important for the upper ocean, for how the ocean and atmosphere interact. So you might expect that if you go into a climate model and make this change, you would see that there is some change, right? So I compared observations taken from a global data set in the ocean to this new parameterization versus the old one. And it kind of looks the same, right? You don't really see a big difference. This is the mixed layer depth. So how deep does that upper layer go? So that's on the one hand, it's a good news because it didn't break the model, which is always something that you want to do. But on the other hand, you really want to make sure that what kind of impact does it leave? So it turns out that if you look at differences and what was affected, the impact was quite dramatic. So there are certain areas like in the Southern Ocean, in the equator, and in the North Atlantic where we did see a really big difference in how this parameter affected the climate model. So that was great news, but this is also kind of old news because although it did make a lot of difference, we still know that it's not as good as it can be. So if you compare on the top right a data set which resolves these processes compared with what the parameterizations say this should be, you can see that in general it kind of looks the same, but there's still quite a lot of differences in terms of the flow. So there are differences in terms of like the large scale. There's also like positive and negative that's missing. So we can still really do better in terms of how we represent these small scale processes in climate models. So for this, I turned into a massive data set, which is an ocean model that resolves about 1 to 2 kilometers globally. So comparing kind of to those models we looked at the beginning, this is about 50 times higher resolution. So I'm going to play this, hopefully, okay, it doesn't look this great on the screen, but I hope you can see that there's a lot of fast variability, and there's also kind of slower variability that's associated with the ocean and the atmosphere. And what I did is I detected these different regions around the world, which were used basically to use as a data set for training. So I'm interested to train a neural network, to train a model which is able to learn what these small scale processes should be from a simulation which resolves them. And you can see that the yellow shading is where we see a lot of fronts. So we've got kind of samples of both regions where we have a lot of activity of these small scale processes and others that are more quiescent. And the idea is to get really a wide range of distribution where we could train something that's quite generalizable. So from the simulation, I extracted physical variables that are relevant for this small scale process, for the submesoscales. I'm not going to use that term too much because it's confusing. But the idea is that if we can, in a parameterization, come up with a function of certain variables that predict small scale processes, we should train a neural network to do the same. So all of these different variables are associated with either physical relationships or other parameterizations that we know are relevant. And the idea is to come up with then a neural network that takes in these different inputs, these different physical variables, and predicts this subgrid small scale flux that we know is super important for the climate model, but we can't come up with just the right equation to describe it. And it works pretty well. So here's a comparison between like the truth, that really high resolution data, compared with the CNN prediction says it will be. Sorry, this is way too big for the screen. And if you look at statistics also, you can see that it does much better than the old parameterization in terms of being able to capture the data. So here's again those snapshots where I compare the truth on the far right, the CNN predictions of the same, and what the physics parameterization said it should be. So that's kind of the previous version. And this here is an example of the climatology, so a seasonal cycle in one of those regions in the Gulf Stream. The blue is the true data, the orange is the CNN prediction, and the green is the physics parameterization. And we can see that the neural network is really able to capture kind of the different dynamical fluctuations over the course of the year. And same for all the different regions that I looked at. So even though we have this widely different distribution across the globe, the CNN is really able to learn how these small-scale processes should act in all these different physical regimes, which is quite phenomenal. So in all of these different locations, we see that the CNN and the true data are staying quite close to each other compared to what the physical or theoretical prediction should be. So one of the questions I was interested in is, I mean, great, the neural network does well, but also why? Why is it so good? And what can we learn from it in terms of physical intuition? So for this, I ran a couple of explainability methods to try to understand really the dependency of these small-scale processes, small-scale ocean turbulence, to these different physical variables that we use as input. So one of the first experiments I ran is I looked at different filter scales of the data, because that also tells us about the physics of the problem, right? Depending on the size or the scale of the process, it will act differently. And I removed one input feature at a time, which is kind of a generic test, but it did tell us a lot, because it turns out that one feature kind of stood out above them all and turned out to be the most important one, which is large-scale strain associated with those large eddies. Turns out that was missing from the previous parameterization, so that was a new result. And then the second test was looking at sensitivity in terms of gradients. So how sensitive is a certain output to a certain input? And what that tells us is about local relationship between inputs and output features. And once again, there was kind of one feature that stood up about them all, which is the depth of the mixed layer. So how much turbulence is in the upper layer. So this is really the same story that we should have suspected, really, which is that these small-scale features are affected both by larger-scale mixing as well as very small-scale mixing. And this is a way for us to get better physical intuition and better understand how we should structure our climate models also if we wanted to put in an actual equation into the model. So future directions in terms of what, I just started like 2 weeks ago. So what my lab is going to be doing at MIT is I'm planning to take this really to the next level and try to see how we can use new forms of data in order to try to improve our understanding of small-scale processes and how to simulate them in the climate models. So there's a new satellite mission that just launched a few months ago. It's called SWAT. And for the first time, it's going to be measuring the ocean at a resolution we've never had before, so about 1 to 2 kilometers, which is pretty phenomenal. So that's going to be available soon, and I plan to be using that really to adapt some of my machine learning approaches in order to understand small-scale, real data. Yeah. And then the other is at MIT, there was an ocean model that's been developed called Oceananigans. It has a great name. And it's a GPU-based ocean model. All the other ones are CPU-based, run on Fortran, super old models. And this is really a new approach to climate modeling. And it's able to run at super high resolution and very fast, which gives us new approaches for testing and understanding this multi-scale interaction in the ocean. So if anyone is interested in these type of simulations and understanding also the processes, please let me know. And just kind of a quick note about how you can learn more about climate models. I'm the executive director of Climate Match Academy, which is a summer school that teaches computational tools to understand climate. So we teach climate data, climate modeling, and also the response of the climate in terms of mitigation and adaptation efforts. So if you're interested in this, we already have dates for the summer, and I'd love to talk more about that. So just to conclude, upper ocean dynamics play an important role in simulating the climate systems. And I discussed a physics-based approach and a data-driven approach, how we can understand this multi-scale interaction in the upper ocean. And I'm getting excited about recent advances in observations and open source modeling. Yeah.
Thank you, Abigail. Another fantastic talk. So thanks very much.